All right, let's finish off this PDF, and then we'll switch to a new one in the next video about actually proving these results with mathematical induction. I filled out the rest of the numbers, and to give away basically number 5, which I really already did a while ago, this idea that to get this 70, for example, you don't have to add all these things from scratch. You can just add the old running total, 35, which was all these guys, plus the new one. So it's just adding these two to get this one. And to get this one, you can just add these two. To get this one, you can just add these two. And that's certainly how I did all these things in the table. And I put in a new column. I realized that it was so useful to have a column for the ratio that I'll put in just at least one more time, a column for the ratio. And our main interest now is looking, there's a lot you can do with these numbers, but our main interest is to fill in the closed formulas and see if we can guess those. We want to guess a formula for the closed formula for the e's. There's a lot of hints already, and again, this is your last chance to stop and try to guess it on your own if you haven't already. 0th power, 1st power, this is n squared modified, this is n cubed modified. This is going to be something to do with n to the 4th. We've got this pattern of multiplying consecutive numbers on the top of a fraction and multiplying consecutive numbers on the bottom. And of course, this has a famous notation. This can be written as 3 factorial. So I'll just write it that way. I kind of like leaving it expanded out to show the similarity between the top and the bottom. They're both 3 numbers multiplied together, 3 consecutive numbers multiplied together on the top and the bottom. We could really guess this guy, I think, but let's do what we did before. The ratios here don't really make a lot of sense here until we get to 0, and then we get 1/4, and then we get 1/2, which is 2/4. 15/20 is, anyone? 3/4, you bet. 1 is 4/4. 70 over 56, not too hard to reduce that to 5/4, 6/4. Okay, this is really making a lot of sense. So they were halves, then they were thirds, now they're fourths. That should be exactly 2, yep. And 9/4 if you reduce it, not too hard. Okay, so now, and then what is this? This 9, that's 12 minus 3. So the ratio is just n minus 3 over 4. Okay, well, in other words, that means that the actual thing we want to calculate is all this thing. Ooh, the magic of copy and paste. Whoa, that didn't work too well, though. Just made it go off the page. Okay, times exactly what we've got left over. So this was, let me write it out, right? This was 3 times 2 times 1. 3 times 2 times 1. Okay, and then just multiplied by 4. Okay. So now the pattern's pretty clear. We've got 4 numbers starting with n going down, 4 numbers starting with 1 going up. This does have this nice abbreviation, 4 factorial. Okay. So now I think we can guess these guys for fn and gn. This is going to be n minus 1, n minus 2, see if it fits on the page here, n minus 3, oops, sorry, n minus 3, n minus 4, and then all over 5 factorial. And then this one, oh yeah, it's getting hard, finding it hard to fit on the page. Sorry, it's kind of flashing in and out, I know for you. Okay, same deal, but with 6 things on the top and 6 things on the bottom. It's probably going to flash. Yep, it's going to disappear, but I'll bring it back. Don't worry. It's getting very wide for this screen, unfortunately. Even at the small scale. I hope this is visible. I know this isn't incredibly great visibility with this size of characters. Okay, so we've got some really good guesses here. And not too hard to verify this. One thing you can do with these, another hint. Ooh, you know, sometimes when I do this with students, I remember, and I just totally forgot when I wrote this up. This explains the zeros. How many zeros are you going to get when you have n over 1? Well, just when n equals 0. Well, when it's n times n minus 1, oh yeah, if n is equal to 0 or 1, it's going to be 0. Here, if n is equal to 0 or 1 or 2, it's going to be 0. Here, if n is 0, 1, 2, or 3, oh, okay. So this thing is going to start with a whole bunch of zeros. It actually makes those zeros that seem kind of filler or kind of wasteful or boring, it makes them have to be there. That this is going to vanish when n is any of those numbers. That actually, I should have put that in as another hint, because it leads you very directly towards guessing, hey, if like here, for example, this is the first one we had to really guess, hey, what's a cubic that automatically vanishes when n is 0 or 1 or 2? It's got to be a product of n times n minus 1 times n minus 2. That is a big hint, and I regret not putting that in. Okay, so in any case, it explains it. And then what happens when n is 6, what do you get? You get 6 times 5 times 4 times 3 times 2 times 1 over 6 times 5 times 4 times 3 times 2 times 1, which is the factorial. Oh, of course it gives 1. And then when n is 7, you get 7, 6, 5, 4, 3, 2, 1 over 6, 5, 4, 3, 2, 1. Okay, so the only thing it doesn't cancel is the 7. Okay, so this is, and you can check the other values if you want, but this, we're right on the money. Okay, so probably, depending on what you've seen, probably you've already realized, hey, wait a minute, this is something familiar. This is Pascal's triangle. Okay, it's not presented in the symmetric form that it usually is, but, and of course, ignore the fractions here. Actually, I think we can now kill those. Okay, so now we can see 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Okay, so I'm not going to assume you know very much about Pascal's triangle, but if it is familiar to you, you probably were already recognizing these numbers. It's just kind of shifted over. So this is one cool way to generate Pascal's triangle. Just start with a sequence of ones, and then just continually do repeated addition, and that fills out the the columns, which are usually drawn diagonally, of Pascal's triangle. And these formulas have various shorthand notations, which I'll talk about at the start of the next PDF, in the next video. They're the binomial coefficients. They show up everywhere in mathematics, in binomial expansions, in combinatorics problems, counting, probability, all kinds of things. But I think it's kind of cool that they come out of just this very simple procedure of let's do repeated summing over and over and over and over again. In order to get this to be exactly the right formula, so this is often written, for example, as with this funky notation, kind of looks like a fraction but with no bar. This would be written as n choose 6. So let me write that out, n choose 6. To get that to exactly match, that's the real reason I had us start counting at 0 and ending at n minus 1 with our sums, because otherwise this wouldn't work so perfectly. All right, so we're going to get a little bit of a different perspective on this in the next video. Oh, and if you want to do the important stuff that's at the bottom of this PDF, I'm not going to do it in the video. I started the neat stuff. We did the important stuff. There's some really cool stuff to think about here, but I'm not going to actually do any answers to it.